All right, greetings everybody. Today we are going to practice not only the ideal gas laws, but additionally the combined gas laws. So um, in the question, it's not going to tell you which formula to use. You just need to look at the different variables that are presented and determine if we are going to use the ideal gas law or the combined gas law. So let's go to the first problem. All right, so let me get my highlighter out. Let me zoom in here. And let's do the first one. Let's do red. A gas sample contained in a cylinder equipped with a movable piston occupied 300 milliliters at a pressure of 2 atmospheres. Looks like it's starting to catch up a little bit here. We're having some lagging. All right, there you go. We're all good. What would the final, that's a key word, final pressure if the volume were increased to 500 milliliters at a constant temperature? All right, so we have the word final. We have two different volumes. Let's go back. So in the ideal gas law, we only have one volume. In the combined, we have two volumes because in the combined gas law, we're measuring a change that's occurring. So let's go back here. All right, so when we have our first volume, so our V1, let me make that a better color. Our V1 was 300 milliliters. Our pressure, our first pressure was 2.0 atmospheres. What would be the final pressure? So we don't know. We're going to put a question mark, but we do know that our V2 or our ending volume was 500 milliliters. So think about it for a second. Oh, and temperature, T1 and T2. Let's just put the number 1 just because it stayed constant. It doesn't matter. You could just leave it blank if you wanted to. But think about it. The pressure, so we have gas particles bouncing around. We have 2 atmospheres of pressure, which is more than that of sea level. And our volume increased. What happens when you make the playground, the perimeter of the playground, a little bit bigger? And the temperature stays the same, meaning the average kinetic energy of all those little gas particles are staying relatively the same, averaging the same. Well, it's going to take longer for those gas particles to move from point A to point B and hit those container walls. So we should see a decrease in pressure. Let's see if our prediction is correct. So let's set up our formula. We have our P1 is 2 atmospheres, and it's really important that you keep your units. Our V1 is 300 milliliters. Temperature T1, and then T2, since it was constant, just scratch it out. We are looking for P2, and our V2, our volume, our ending volume was 500 milliliters. All right, so it's really important that you keep track of your units. I say that because when we use the ideal gas formula, it is very unit dependent, meaning that you have to be in the correct units when you're multiplying, dividing specific numbers. However, when using the combined gas law problem or gas law formula, as long as the units, as long as pressure is in the same units as the starting and ending, as long as volume is in the same units, and as long as temperature is in kelvins, you are good to go. So let's double check. Atmospheres, we're going to look for, our answer is going to be in atmospheres. Milliliters and milliliters, we're good to go. So when you see a number on the opposite side of the equal sign, what we're going to do is we're going to move diagonally. So when you are trying to, we're going to cross multiply. So to get rid of this 500, I can't just move it over left from right to left. The only way I can do so is to move it diagonally. So we're going to put the 500 down here. Oops. Okay, that's going to scratch out. So let's make it look a little bit nicer. 2 atmospheres. Divided by 500. So our P2 is going to be in atmospheres because milliliters and milliliters cancel out. And let's see what, let's get Pinky out. Get your calculator. 2 times 300 divided by 500 is 1.2. All right, so box in your answer. Is our prediction correct? Did it drop from 2? It did. It went to 1.2. Makes sense. All righty, let's see if we can go to problem number 2. A chemist is preparing to carry out a reaction at high pressure that requires 72 moles of hydrogen gas. The chemist pumps the hydrogen into 12.4 liters of a rigid steel container at 25 degrees C. To what pressure in atmospheres must the hydrogen be compressed? So we know that we're looking for pressure, question mark, in atmospheres. Do we have anything else? We have some other stuff here. So our volume is 12.4 liters. Our temperature is in 25 degrees C. Okay. And then we have moles, which is 72 moles. All right, so let's see which formula we're going to use. We have moles, check. We need pressure, we need volume, check, check, check. We have temperature. It's in Celsius, so we need to move it to Kelvin. The last number that we don't have is R. And since we're in atmospheres, we're going to be using the 0.0821 R. If you were in kilopascals, you would be using the 8.31. Okay. All right, so let's change our temperature to Kelvin. So we know that we need to add 273 to that because Kelvin is always 273 above Celsius. So what does that turn into? What's 5 plus 3? 8. What's 2 plus 7? 9. All right, so we have that much in kelvins. And the R that we're going to be using that is not present, but you just need to know which number to use, 0.08. Oops, it is 8 1. That's going to be our gas constant. All right, so let's set up our formula. We have P in atmospheres. Pivnert, our volume is 12.4 liters. Just a reminder, when you're this formula for ideal gas laws is very temperature dependent. The volume has to be in liters. Temperature always has to be in Kelvin, no matter what. We're going to be using this 0.0821 for the R. And since we're using atmospheres, that's what we're going to use, okay? The number of moles is 72 moles. R is going to be 0.0821. And then temperature is going to be 298 Kelvin. How do we get P by itself? Well, 12.4 needs to go on the other side of the equal sign. And whenever you do that, you have to cross multiply. So this 12.4 is going to go down here. Going to scratch that out. So now we're going to just do 72 times 0.0821 times 298 divided by 12.4 liters. Our pressure in atmospheres is a whole heck of a lot, 142.06 atmospheres. That is a whole lot of pressure because we got a whole lot of moles. Okay, it's really not that hot because 25 degrees Celsius is room temperature. Okay, the volume and the number of moles is where it really cranks it up in terms of pressure. So we've got a whole lot of groups. Remember, a mole is not a molecule. A mole is a group. Remember, just like we group dozens, like 1 dozen is 12. Well, remember, we got a whole lot of atoms. 1 mole is 6 times 10 to the 23rd atoms or molecules. So multiply that by 72. We got a whole lot of molecules in a fairly small space. Okay. All right, that's number 2. Let's go to number 3. Let's see if I can zoom in here. All right. Let's go back to red. A 280 milliliter sample of neon gas exerts a pressure of, there's our pressure, 660 torr at 26 degrees Celsius. At what temperature? Wait a second. They gave us a temperature and we're looking for another temperature. Red flag. Okay, we have a temperature and they're giving us they're giving us a temperature and we're asked to solve another temperature. We're definitely going to be using PV over T equals PV over T. And remember, as long as you can use it is not so specific as long as the units are the same for pressure and volume on both sides. Okay, so let's use our first pressure was 660. And our first volume was 280. What was our first temperature? 26 degrees Celsius? You need to add that to 273. So let's add 273 to that. Because you need to put in kelvins. All right, and then what temperature? So we're looking for T2. that is also in kelvins would exert a pressure of, here's our P2, 940. And then the volume is 440. All right, so think about it for a second. The pressure went from 660 to 940. Pressure went up, okay? Gas molecules are pressing on the container more frequently. In addition to that, the volume got bigger. So not only did our perimeter of the playground get bigger, everybody inside is bouncing around even faster and causing more pressure, even though the volume is getting bigger. One can only assume that the temperature went way up for this to occur. So let's rearrange our formula. Now remember that the only way I can move things when I'm using a fraction and there's an equal sign and I have two fractions on either side of the equal sign, look at that, bam, 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 okay? You can only go diagonally, okay? So in addition, my variable that I need to solve for is on the bottom. So I need to get it to the top, but I can't just go to the top. I need to go to the top and diagonal. So this is gonna go, T2 is gonna go over there, okay? And what it's gonna look like is this. Let me just be very, let me show every step. So I have 660 to 80. What's 26 plus, here, let's do steps here. Let's just, and then what's 26 plus, so what's 6 plus 3? 9. So 2 plus 7, 9. And then we have a 2, it's 299 Kelvin. And then remember, we have the 940 over here and the 440. Now I have T that I need to get by itself. Where does 299 gonna go? 299 is gonna go up to the top. What about 660 and 280? Where are those gonna go so that I can get T by itself? Both of those are gonna go to the bottom. So let me rearrange my formula to make it look a little bit nicer. And you're gonna get pretty good at moving the checkerboard around. So let me change my pen. So now we have 299, 940, 440, and we have 660, and then we have 280. So now that we've rearranged the formula to solve for T, okay, let me just double check to make sure that's all right. 660, 3. All right, looks good to me. Hopefully I didn't make any boo-boos. Let's get our handy dandy calculator out. 299 times 940 times 440 divided by 660 divided by 280. Well, would you look at here? The temperature went way up. 669.19 Kelvin. It started at 299 and it went way up to 669. That makes a whole lot of sense because the playground got bigger and somehow these little kids, these little gas molecules are pressing more frequently. So there's only one way to answer that is that the temperature went way up. They're actually moving faster now to to make up for the increase in volume and then some. Beautiful. Let's zoom and go to the next one. Oopsie daisies. All the way down here. There we go. All right. To what temperature must 6.5 moles of gas? Whoa, 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 whoa. I just saw a context clue. Which formula has the word mole in it? This one does. That one right there. Yeah, that one. Pibnert. It's heated. There's my volume in order for it to exert a pressure. All right. So remember, when we're using the Pivnert, if we're using atmospheres, we got to use 0.0821. No matter what, you have to use kelvins in both formulas. All right. So here's our pressure is 7.5 atmospheres. Is our volume in liters? Yes, it is. We can use it. 15 liters. Number of moles is 6.5 moles. The R that we're going to use is 0.0821. And then at what temperature? Remember this temperature, the answer is going to be in Kelvin. All right, so how do we get T by itself? We got to move these downtown Charlie Brown. So let's get T by itself. Remember, T is going to be in Kelvin. And then we're going to have 7.5, 15, 6.5, and then we're going to have 0.08821. All right, so let's do this one. Get your calculator out. 7.5 divided by 15. Oops, oopsie daisies. 7.5 times 15 divided by 6.5 divided by 0.0821. And our temperature is 210.8 Kelvin. What happens if I was being Mr. Tricky here and asked you to put the answer in Celsius? Oh. Remember that Kelvin is always 273 degrees higher. So for us to go down to 210, that means we've got to go down the same amount in Celsius. Okay, so how much did we decrease by? So if 0 degrees Celsius is 273, and we ended at, how much did we go down by? So let's do some quick subtraction. We went down negative 62.2. That means we've got to go down negative 62.2 over on the left-hand side. Make sense? Kind of? Okay. So we can say, or it's negative 62.2 degrees Celsius. I'm going to misspell Celsius. There you go. Clutch. Make sense? If it doesn't, let's do some more. Zoom, please. Get it? Zoom on Zoom. Some oxygen is collected in 0.25 liters container at 25 degrees C at 720 millimeters of mercury. How many moles? Oh, context clue. Moles, Pivnert. Okay. Remember, I did not provide you an R constant for torr. So that being said, we've got to either convert our millimeters of mercury into either kilopascals or atmospheres. Which one do you think is easier? I think it's easier to use atmospheres myself. If you picked kPa, shame, you brought shame. How many, oh my gosh, Murphy, you're asking us to solve for moles and grams? How could you? All right, so let's use the Pivnert. It is very, what is the right word? Unit dependent. So the pressure that they gave us is 720 millimeters of mercury. The volume is 0.25 liters. That looks good to me. Temperature needs to get fixed because currently it's at 25 degrees C. Remember 273. Kelvin is always 273 degrees more, so we need to add 273 to that, which would be 298 Kelvin. That's all fixed. We're going to use atmosphere, so we're going to use 0.0821. And then what we're looking for is our number of moles. Okay. We've got to fix this millimeters of mercury. So millimeters of mercury on top, millimeters of mercury is going to go on the bottom, and top to bottom, top to bottom, top to bottom. What's the ratio of millimeters of mercury to atmosphere? Well, there's a 1 atmosphere to 760. So we're going to say 1 atmosphere on top, 760. Now we are not cross multiplying here, no equal sign. So if you go down, you're dividing. So let's do 720 divided by 760. And we get 0.95 atmospheres, pretty much almost 1 atmosphere. So here's all the numbers. Let me show you what we're going to do here. We're going to have Pivnert is our formula. We need to get N by itself. So what are we going to do with R and T? They're going to just go diagonally, which leaves us with P V over RT. So let's just plug and chug now that we have all the numbers in the correct units, and it should be good to go. So that's 0.95 atmospheres. Our volume is 0.25 liters. The R is 0.082. Oops, daisies. There we go. And then our temperature is 298 Kelvin. Remember, we're going to use the 0.0821 because we're using the atmospheres. And let's do this. 0.95 times 0.25 divided by 0.0821 divided by 298. Oh my gosh. Oh my gosh. We have 0.0098 mole. I don't think I gave myself enough room. Let's make a little bit of line here because that's the answer for the first part. Moles of oxygen, which is O2. So let me circle that. That's the answer for the first one. And let's see if I gave myself enough room. The question also asks how many grams of this. So we're going to go a quick mole to gram conversion. So we have 0.0098 moles of O2. Moles are on top, moles are going to go on the bottom. So for every mole of O2, how much does that weigh in grams of O2? The reason why there's a 2 there is because it's a Super 7. Have Super 7 diatomic molecule, have no fear of ice cold. On the periodic table, each oxygen weighs 16. 16 plus 16 is 32. So let's take this number, 0.0098 times 32. How many grams is that if we were like actually like weigh it? Okay, which is hard to do for gas because won't go there. 0.31 grams. Ta-da! All right, let's go to number 6. You're like, how many questions are there? Well, just look at that little YouTube timer. See how much time you have left in the show. A gas is a volume of, there's our volume, we have a temperature, we have an atmosphere. Calculate wait a tick, there's 2 volumes. If there's 2 volumes, then we're going to use the combined gas law formula. All right, so our first volume, let's do our PV over T. And then our PV over T. Our first volume is 240. Now, it doesn't matter about the units for PV over T as long as they're the same on both sides. You can't see my finger, but on the same of both sides. We're looking for volume, so we need to put a V2 question mark. Go back to blue. My boy blue. It's 25 degrees Celsius. Add 273 to that. 298 Kelvin. And then we have 0.789. Wait a tick. It says calculate the volume, but we have 2 empty spots over here. Need I remind you that STP is, side note, standard temperature and pressure. The temperature is 0 degrees Celsius at 1 atmosphere. Okay, so we can put the atmosphere in there because the atmosphere matches this atmosphere, so the units are good. But we got to fix that 0 degrees Celsius. Add 273. All right, so now we've got to get V by itself. So what am I going to do? I'm going to start cross multiplying. I'm going to bring that 1 down here if it's going to do anything. And then I'm going to bring that 273 at the top. And let me rewrite this out. We're going to have 0.789. Then we're going to have 240. And then we had Mr. 273 join the party. 298. And then, not to confuse anybody, but one still count. Solve for our volume. And remember, since we started with milliliters, we are going to end with milliliters. You can use milliliters in this formula, but just remember what you start with is what you're going to end with. Okay, so let's get Pinky out. Pinky in the brain times 273 divided by 298 beat you. 173 milliliters. What happens if I ask for liters? King Henry died drinking chocolate milk. What do? Okay. What do? Okay. There we go. Perfect. Looks good. Alrighty. Next. It never ends. The problems, they never end. It is desired to obtain a volume of 1 liter of nitrogen. I'm going to go a little bit faster for the last three. 100 degrees Celsius, 640 millimeters. How many? What the moles? How many grams? Well, there's only one formula that talks about moles, and it's that formula. Nope. Not combined. It's the Pivnert at the top. So let's do it. We have volume. Is it in liters? Check. Is our temperature in Kelvin? Nope. So we need to add 273 to that. Do not use your calculator for this one. 373 Kelvin. Check. We have pressure, and it's at 640 millimeters of mercury. You can also call this torr, because Torricelli use millimeters of mercury. So I'm going to get rid of millimeters of mercury because I want to go to atmospheres. Millimeters of mercury on the top, millimeters of mercury on the bottom. Remember that it's, so for every 1 atmosphere, it's 760. Well, I'm going to give that 80%. Let me see what happens. 84, close enough. 0.84 atmospheres. Less than 1 atmosphere. What else are we looking for? R, since we're going to use atmospheres, it's going to be 0.082. Dang it. Oh, sugar. 0.1, and then we're looking for number of moles. So remember our formula is Pivnert, and then we're going to rearrange it to look like this. Okay, so let's rearrange it. The number of moles is PV. So pressure is 0.84 atmospheres. The volume is 1. The R is 0.0821. And then the temperature is going to be 373. Let's find the moles for this. 0.84 times 1 divided by 0.0821 divided by 373. We have a mole of 0.0, let's do two decimal places. Now, we just answered the first one. Let's answer the second part. Let's go moles to grams. 0.03 moles of nitrogen. Remember, nitrogen is a diatomic. You need to know your super sevens. Moles on top, moles on the bottom. Top to bottom, top, to bottom. On the periodic table, nitrogen weighs 14. There's two of them, so we're going to say 28 grams. 0.03 times 28. That was crazy. We're going back to 0.84. This was just a quidink, but 0.84 atmospheres and 0.84 grams have nothing to do with each other. Don't even look at it. Don't even look at the 0.84 atmospheres. Those spooky how the numbers work sometimes. All right. Oh man, I can never find. There's so many buttons that look the same. All right, two more. Let's go. You can do it. I believe in you. Volume, liters, temperature, degrees Celsius, atmosphere. Calculate the pressure. If the volume, volume changed. So we're going to use PV over T equals PV over T. There's two volumes and the temperature changed. What? Oh my gosh. All right, so our initial pressure is 1 atmosphere. Our initial volume, dang it, is 4.2 liters. And the temperature is 60, but you have to add 273 to that. Okay. And then calculate the pressure. So we're looking for pressure. If it's changed, it got bigger. The playground got bigger. We went to liters, so it went from 4.2 to 5. The perimeter got a little bit bigger. And the temperature went way down. 27, we got to add 273 to that. Oops. Okay. And then let me use a different color. You know what? This is really upsetting me. Okay. Red and black, friend of Jack. P2. All right. We need to get our ending pressure by itself. So red and yellow, kill a fellow. All right, so B5 needs to go down here, and all of this stuff needs to go up there. But before we do that, let's just figure out what this is. What's 6 plus 270? What's 60 plus 273? So that is really 333. Oopsie daisies. This is really 333. And then what's 27 plus 273? That kind of looks like 100. 300, I mean. Don't you glitch out on me now. Kind of looks like 300 to me. All right, so let's move them. Crisscross applesauce. Ka-chow. Ka-chow. Not kachuga, but ka-chow. All right, so we've got the 1, we've got the 4.2, we've got the 300, and then we have the 333, and then the 5. And remember, we started with atmospheres, so therefore we are going to end with atmospheres. All right, so 1 times 4.2 times 300 divided by 333 divided by 5. And our atmospheres went down 0.76 atmospheres. Let me just double check because that's a lot of numbers. Yep, okay. Even though, so the playground got bigger, which is going to decrease pressure, and the temperature went down. The average kinetic energy went down. So it's got 2 strikes against it. Pressure is going to decrease if the temperature goes down and the volume gets bigger. Okay. All right. So there's our answer. Oh, man, black really just pops on this white background. All right. Last one. I saved the best for last. We have grams. Let's go back to black. We're back in black. We have temperature. We have pressure. What's the volume? There's no change. So we're going to use PIVNERT. What's the pressure at currently? 323 milliliters of mercury. Let's get that to atmospheres. All right, so we're going to do 760 for every 1 atmosphere. Looks about half to me. So 323 divided by 760 is 0.425 atmospheres. We are looking for volume. We're going to use 0.0821 since we have atmospheres. That's the gas constant that goes with atmospheres. Temperature is 155 degrees C, so we need to add 273 to that. Uh, 155 plus 273 is 428 Kelvin. Check, check, check. And we're solving for volume, but we were given grams. Son of a biscuit. Grams of what? Hydrogen? When have you ever seen a hydrogen by itself like that? It doesn't happen. It's a diatomic. You need to know your diatomics. Hydrogen gas. All right, grams of hydrogen gas on the top. Top to bottom, top to bottom, top to. Grams of hydrogen on the bottom. And we're going to go to moles. Okay. 1 hydrogen is 1 gram. 2 hydrogens is 2 grams. So we are going to cut this in half. Can anybody do this without a calculator? Not me. Moles. Okay. All right, so let's rearrange the formula. Originally we had, you know what, since we got room, let's use it. Can everybody see? We have PIV NERTs. Do we have pressure in atmospheres that match the R gas constants? Check. Is our volume, oh, that's what we're solving for. Temperature in Kelvin, check. Is N in moles and not grams? Check. So let's rearrange the formula for nRT over P. So the number of moles is 0.001. The gas constant is 0.0821. Temperature is 428. Pressure is 0.425. And then remember, volume is going to be in liters. So let's get our calculator out. 0.001 times 0.821 times 428 divided by 0.425. And it's going to be 0.83 liters. And that is that. I sure hope I was recording. This was a long session. Cheers, everybody.